Thank you. All right. As you work, ew, this looks like. Alrighty, I have no concept of time, but I think it's been at least like 1 or 2 minutes. So what do we think about number 1? IR? Okay, why is that? It has a different H, yes, but that's more NMR, right? So functional groups. So we have an OH here versus a ketone here. Those would give you different IR peaks. What else is different? The double bond. So a lot of people forget that an alkene versus an alkane are 2 different functional groups. So, ta-da! So we all agree that it's IR? Haha, I tricked you. Okay. So, all right. So it's actually going to be both. And the reason is you guys are absolutely right. There are different functional groups. But as someone mentioned, there is a different hydrogen in there. So if I zoom in here, we have 1 hydrogen here that's connected to a double bond versus 2 hydrogens here that are connected to a single bond. Plus, we have this hydrogen on the oxygen, and we don't have a hydrogen ketone. So for this one, we actually can say both. Any questions? Exactly. So in that case, they have different like carbon hydrogen frameworks. You can think about it. So the skeleton is different. Okay, what about the second one? NMR, exactly, because the only thing that's different is where the OH group is. So this one is, what? Is it primary, secondary, or tertiary? Secondary, cool. Versus the other one is primary, cool. So we're going to use NMR. And what about the third one? Ooh, okay. So someone said, a couple people said IR, a couple people said both. So let's look at it. The difference here is an OH versus an NH. So that is a functional group difference, right? But why would you say both? Cool. Okay. We don't care about that. And let me explain. So in the first example, we had like a big difference, right? It was 1 hydrogen on a double bond versus 2 hydrogens on a single bond. And then we had an OH versus nothing, right? In the third example, we have a nitrogen and an oxygen. Both of those are heteroatoms, right? So on an NMR, they would be pretty close. So the reason we're only going to use IR on this one is because those signals would be really hard to distinguish. And that's the only difference they have. So theoretically, yes, we could use both, but it's going to be a waste of time to use NMR because they're so close. Does that kind of make sense? No, that is absolutely correct. So the reason number 1 is different than number 3 is because number 1 has a really big difference versus number 3, mostly a functional group difference. The hydrogen difference is real. Questions, comments, concerns? Cool. All right, so that was just a little bit of review about the difference between IR and NMR. So where we ended last time is counting signals. So we're going to do a couple more of those. And what is the first thing we look at when we're counting signals? Symmetry. Awesome. So I already do the line of symmetry for this one. So first we're going to do hydrogen NMR. So these 3 hydrogens, are they symmetrical with any other hydrogens? Yes, the other methyl, right? So what is the integration of the blue signal? 6. Okay, perfect. Is this carbon going to have a hydrogen signal? No. Perfect. What about this one? Yeah. Oh, Yes. And is that going to have a symmetrical hydrogen? Yes. We did a very similar one. Oh, maybe we started it. And then these last ones. So what's the integration of the red hydrogen? 2. What about the green one? Super. So how many hydrogen signals do we have? Cool. Now let's do carbon. We have 1 carbon signal. We actually have this carbon signal. And then these ones. Last but not least, these ones. So how many total carbon signals do we have? 4. Any questions about how I did this one? Cool. I'll leave it up for a second. The next one we're going to do is kind of a more fun one. All right. So what's the first thing we look for? Symmetry, yes. Does this have any symmetry? Wrong. Haha, I got you. So, yeah, what? Kind of, sort of, you're on the right track. Does anyone else want to take a, yes. What was that? Not really. Shift, yeah. I know what you're talking about, but we're not going to do that. Do you have... Exactly. So this doesn't have symmetry across the whole molecule, but it does have internal symmetry. So these are symmetrical. So as she said, all of these hydrogens will be exactly the same. Kind of like what we saw before. And this is getting really messy, so ta-da. And we know that the integration is? Yes. Cool. Does this carbon have a hydrogen? Yes, it does. Bam. And the integration is? Cool. And do we have any other signals? Yes. Ta-da, right here. And surprise. And this one is also 1H. You guys caught it, but a lot of people forget that aldehyde hydrogen. So look out for your implicit hydrogen. Any questions on this one? Yes. Yeah.
Oh.
Yeah.
But
okay, great question. So why do you think it would count differently than the other one? It would be, yeah. So it would be exactly the same. So let's start there. Oops. We have 1, 2, and then these guys are the same. So how many total hydrogen signals do we have? 3. How many carbon signals? 3. Cool. And I didn't know this thing was in the way. Go away. All right. It does, and it has internal symmetry. So I will highlight that. That's really ugly, but I'm not going to rewrite it. Okay. So since you guys did that one really well, let's go to one that I think he did in class, but I really like to do. Ta-da! So now we have to actually look at things kind of in 3D. So let me go ahead and draw in this hydrogen here. So do we have any symmetry on this guy? Yes. Where do we have symmetry? Down the middle, which way? Okay, cool. And is there anything else? Yes. Which way? Exactly. So I'm going to just draw right through this. So this one's pretty cool because we can kind of just cut it up into quadrants, right? And we know all 4 quadrants are exactly the same. So this carbon is exactly the same as this carbon, which is exactly the same as this one, which is exactly the same as this one. So we could also say that the hydrogens on each of those carbons are also exactly the same, right? So, bam, bam. Okay, so you guys are saying all of those are exactly the same, and yay! Okay, so that was kind of a trick. So why would they be different? Why would they not be the same? What do you think? Perfect. Okay, so let's erase that. I'm sorry if anyone already wrote that down. Okay, so let's do the wedged ones. And so if it's wedged, what is it seeing in its environment? Exactly. So it's going to see, or they're going to see OHs, right? But the ones that are dashed, what are they going to see? All the hydrogens. Exactly. So we could say that those are 2 separate signals, right? So what's the integration for the green signal? 4. What about the blue one? 4. Cool. Yes, it would, because we also have this yellow one. So how many hydrogen signals do we have? 4! Everyone forgets the OH. Don't forget this little guy. So how many do we have total? Oh, I already said that. Oops. So we have 4 H signals. What about carbon? Yep, we just have 2. Is that yellow too light to see? Oh, mixed signals. I'm going to cover it again anyway. Ta-da! So is that 3D thing kind of okay? All right, perfect. So we are going to use that example to segue into a different concept, which, of course, I didn't give any room on the handout to do. And add a page. Okay, do the words homotopic, heterotopic, enantiotopic, diastereotopic, do those at all ring a bell? Cool. Okay, so let's start with homotopic. What's that mean? Exactly. So you can kind of tell by the name homotopic, they are the same signal. And the opposite of that would be heterotopic, which would be different signals. Okay, so these are very vague terms, right? They're big umbrella terms. And an example I can give you is, let's say we have this, right? A simple carbon chain. I can have 1, 3, 3, 1, 2. So I already spoiled it, but we have a line of symmetry down the middle, right? So this set of red and this set of red are exactly the same. Do we agree on that? Yes. So the relationship between the red ones is homotopic. And so these pink ones, same exact thing. It's one signal. They're on the same carbon, so they're also homotopic. Heterotopic, however, can be super duper broad, right? I mean, they're both super duper broad. But let's say we have the same exact carbon chain. Now we're comparing the pink to the red, right? They're just completely different from one another. Okay, so anytime a signal is different, it's considered heterotopic. That's usually fine for students. Where it gets kind of spicy is when we have an antiotopic and diastereotopic. Do those words ring a bell at all? That's so fair. But for anyone who does kind of know, can you tell me anything about them? I literally couldn't have said it better myself. Awesome. So I will repeat that though. So this is basically when we have the same signal, because it is a specific type of homotopic, but if we change the hydrogen, we get enantiomers. And if that sentence makes no sense to you, that's okay, because I'm going to show you what I mean. I am going to scroll up a little bit. Okay, so let's say we have something like this, right? And I care about those two hydrogens. Does anyone remember what a chiral center is? Yes, so what's a chiral center? Exactly, a carbon that has 4 unique groups. Do we have a chiral center here? No, but we do have something called a potential chiral center. So I'm going to put a little P here. So a potential chiral center is a carbon that has 2 unique groups and 2 hydrogens. And the reason it's a potential chiral center is if I replace one of those hydrogens, we get a chiral center. So let's zoom in a tad and let's call this HA, HB. Give it some wedges and dashes. You don't have to know what mechanism or anything or what reaction this is for now. Let's just say we replace HA with an OH. Ta-da! Is this going to be any different than if I replaced HB with OH? Ooh. Okay, let's draw it out. Something people always tell me is like, I thought I knew the answer, and then you made that face. And I'm like, well, exactly. So what is their relationship? Enantiomers, yay! And in case anyone doesn't remember, enantiomers is basically just when you have one R and one S. So you have a difference in the chiral center. That's an oversimplification, but for this class, that's fine. So any questions about what I did here? All right. So the relationship between HA and HB is enantiotopic. Cool. So to recap, does anyone want to tell me what is the criteria to be enantiotopic? Awesome. So you need to have a potential chiral center. Perfect. Diastereotopic is where it gets a little bit confusing sometimes. Does anyone want to take a shot at telling me anything about this? Close. Close. Why do you say that? Exactly. Cool. You're on the right track. Does anyone else want to chime in? Exactly. So let's put those pieces together. Diastereotopic are going to give you different signals. Cool. And there are actually 2 different kinds of diastereotopic signals. So I'm going to break it down into, first, let me make a line here. we're going to break this down into chiral centers and double bonds. So like Luke said, we are going to look for something that has two chiral centers or potential chiral centers or some mix, right? So let's say I have this guy. Do we have a chiral center? Yes, we do. Do we have a potential chiral center? Yes, we do. So the difference between an antitropic and diastereotopic is these signals already, or excuse me, this molecule already has a chiral center present. So if a molecule has a chiral center, by default, all of the potential chiral centers on the molecule are going to be diastereotopic. And the reason for that is if we replaced HA versus HB, we would get a set of what? Diastereomers! Yay! Okay, so let's say we replace it with a bromine or something. Takes so long to write out, but that's fine. All right, so these are a set of diastereomers. So what this means is HA and HB are completely different signals. They are entirely different from one another. Yes, you can think of it like that, but I think the easier way to think about it is they're going to be different if you have a chiral center present already. You're looking at a potential chiral center. They already see different things, yes, and if you were to replace one of them, you would get two completely different molecules. Exactly. Yeah. But if you have 10 potential chiral centers, all of them are diastereotopic. So the double bond one is a little bit more straightforward. So let's say we have a double bond, right? And I'm going to draw some stuff on it. Ta-da. And on the other side, for funsies, two hydrogens. So a lot of people get tripped up on this. So this is the way I look at double bonds. I'm always going to cut them in half. Yeah. And I'm always going to say carbon 1, carbon 2. Doesn't matter which one is carbon 1, doesn't matter which one is carbon 2. You get to pick that. All you need to keep track of is one of the carbons needs to have 2 unique groups. And the other carbon needs to have 2 hydrogens. So in this case, the left side, or carbon 1, has a methyl and an ethyl, so it's unique. And here we have 2 hydrogens, so I'll call them HA and HB. So HA and HB, I love that ringtone. If you replace each of them, you'll get a set of, I feel like talking along with the speed that I'm writing is like killing people because it's so annoying. But okay, so these are two completely different molecules, right? So what could we say, or how could we name them possibly? Yes, but E and Z, exactly. So what would this be? Yes, yes, exactly. So we could also say cis or syn. So this is the substituent that is a priority on the left. This is a priority on the right. This is a priority on the right. So they would be Z or cis. And this one would be trans. Cool. You cannot flip flop between the two. That's why these are completely different things. Because you cannot flip flop. Two hydrogens. Yes. So he will try to trick you, because of course, right? Love that for you, right? Okay, so if he gives you a double bond like this, bam, bam, what do we think of HA and HB? Exactly. So if we were to cut it in half, this side is exactly symmetrical. So what's the relationship between HA and HB? We'll get a couple different ones. Homotopic, yes. Because they would be exactly the same. There's symmetry across the whole molecule. Bam, just like that. And just to not confuse you, this is not all. So these are homotopic. Cool. Now, what if I switch it up and I give you this? What's the relationship between HA and HB now? Heterotopic, why? Kind of, but there was no symmetry up here, was there? They're on different carbons, exactly. So they are on completely different carbons. I told you the rules were carbon 1 has to have two unique groups, carbon 2 has to have two hydrogens. These would be completely different, no relationship whatsoever. Ta-da! I think that's all the different examples he can give you for double bonds. So let me zoom out. Take a look. Why is this in there? All right. Any questions? Well, give you a moment to take it all in. And there are some practice problems. Should be like a minute or so. Ta-da! Okay, so now this is on your handout. Yay. So let's call this 1, 2, 5. It'd be so cool if I numbered these from the get-go. All right, so perfect. Think they're exactly the right number of you. I want you all to turn to a partner. Or you can get up and walk around if you would like. And okay, so you guys are going to do number 1. You guys are going to do number 2. You guys are going to do number 3, number 4, number 5. All the way in the back, number 6, 7, 8. I'm sorry to rip you guys apart. 9. You two guys in the back will do 10. Oh wait, just kidding. 8. So you'll do number 1, number 2, number 3, number 4, number 5, number 6. So you guys can work together. If you don't remember what number I told you, just do any number. I don't care. I have no idea. Just do whichever one feels right.
I have a lot of college. The youth. Well, $5 for probably speaks specific. I think they have that same.
Okay, hello guys. Let's get back to that was my war cry. Okay, cool. So, all right. I almost considered doing like the clap thing that they do in elementary school, but I was like, that's annoying. I might do it next time. Whatever. What happened? Oh my gosh, triggered. Okay, so all right. I know that when I get sidetracked, I just can't go back and focus. So let's try to pull it together. So who did number 1? What are you thinking about this one? Well, that's not enough. Why is it homotopic? Perfect. All right. So there is a line of symmetry down the middle. Therefore, this is not a potential chiral center. Everything is symmetrical. So these are homotopic. Anyone disagree? Cool. Who did number 2? Okay. So who wants to be brave and tell me something about number 2? Okay. What was your name again? Van. Okay. What was your name again? Muhammad. Okay. Perfect. There was something that a couple people were confused about, so I do want to talk about it. Is this a potential chiral center? Okay. We're gonna do a poll. Hold on. These are my favorite. Okay. Who says it is a potential chiral center? Who says it's not? Who says it is a chiral center? Okay. So I only kind of tricked you guys. So why is it not a potential chiral center? Yes. It doesn't have 2 hydrogens. And one more thing. Yes. Okay, cool. So he loves to randomly put wedges and dashes in there to trick you. So people look at this and they're like, ah, wedge and dash. But no, those are both methyl groups. Yes, you are right. So this is also not symmetrical, and HA and HB are just on completely different carbons, so they are just heterotopic. Bam. Food number 3. Explain, please.
So
Okay.
there's a line symmetry.
Yes. Yes. Awesome. Okay. So why don't we talk about the double bond? Because double bond equals diastereotopic, right? Awesome. There's always someone who's like, but there's a double bond. I know, but we're not talking about it. So this is diastereo. Nope, I lied to you. Enantio. I just get so excited I forget words. All right, any questions on that one? Cool. What about this one? Who's your number 4? Whole room of people, nobody did it. I'll give you a hint. We did this one already. What? Awesome. Why is it diastereotopic? Perfect. So we have a chiral center, and this is a potential. Sweet. All right. Who did this one? I know I was bad at assigning these, but nobody. Okay, thank you. Awesome. Why is that? Awesome. So one thing that I saw a couple people were kind of confused about is all 3 of these guys are hydrogens. So how is that a unique group? Well, remember when we're talking about unique group, we're only comparing this one to this one. So as long as those are unique to each other, you pass the test. All right, what about this one? Yes. Yeah. Yeah. Okay, I half agree with you. Why do you say diastereotopic? Awesome. So I successfully tricked you. I wanted you to kind of think about that option because it is on a double bond. However, HA is not on the double bond. It's on a completely different carbon somewhere else entirely. So I agree with your first answer. They are heterotopic. Because again, they're just on completely different carbons. Yes.
Doesn't matter if they're
No. So it does have to be on the same side. Because remember what we said, carbon 1 has to have 2 unique groups. Carbon 2 has to have a hydrogen. Yeah, exactly. So let's say, just for practice, we have HC and HT, right? What's the relationship between HA and HC? Heterotopic, exactly, completely different. What about HB and HC? Yes, diastereotopic, because they're on the same carbon, 2 unique groups. What about HB and HD? Heterotopic, exactly, because again, on 2 completely different carbons. Are we kind of sort of okay with that? Okay, yes. Yes, let's just finish 7 and 8 and then we'll go back to 3, okay? I promise. So 7, we already did this one. What is it? Enantiotopic, exactly. I think I heard someone say it. Yeah, because they're on the same carbon and they are a potential chiral center. Perfect. And number 8, what do we think? They're the same. It's homotopic. I heard a couple people saying it. It is symmetrical. So these groups are exactly the same. So these are homotopic. Perfect. All right. So number 3, really quick. The reason we kind of just threw out the double bond is because it's kind of here to trick you, right? Because he wants you to think double bond equals diastereotopic. However, the hydrogen is not on the double bond. So the hydrogen, double bond only counts if the hydrogen is on it. Okay? All right. So we kind of went over time. I'm really, really sorry. But have a good one. If you have any questions, please let me know, and I will see you next week. You're very welcome. Because I have part of my dog. No, I just observe it. Yeah. Don't tell anyone, but I'm only there like 20%. So